Good afternoon, students. Can you see my PSpice screen?
Yes, sir. Good morning.
Okay. Well, it's afternoon, young man.
Afternoon, sir.
Okay. As you can see, your assignment is on the screen. Okay. People who should be hearing this are not here, but anyway, they should be here. I want to point out something to you. Okay. So here's the schematic. Most of you did this well. I haven't looked at all the assignments yet. Okay. Well, those I've seen. What I've seen though is some people not presenting material well, even at this late stage of the game. Okay. Let's now go to the simulated sine wave. All right. Now, notice I have the simulated sine wave. Okay. I can improve this by changing the scale from let's go from -15 to +15. And what does that do for us? It gives us less space it's not used. And if I went from -12 to +12, that'd probably be better. Okay. It gives me a better graph because less space on the graph is unused. Now, notice initially I have not reached steady state. In other words, my signal is still changing. My signal is still changing, and yet some of you all cut off about here. Okay. Well, clearly you can't cut off here because you're still changing. You gotta wait until you reach steady state. Okay. And some of you all just gave me a graph and all these cycles bunched together. Well, you can't read that either. The whole purpose of a graph is so that you can read it and get intelligent information from it. Okay. Now, I didn't ask this on the homework, on the assignment. How can I tell the frequency from this graph? How can I tell the frequency from this graph?
I'm not sure, but what I do know, we know the time and we know the voltage.
Okay. How can I tell the frequency from this graph? Wow.
Could you write down the amplitude to be equal 1 over RC?
Why? What theory tells you that? What theory tells you V, because you said amplitude, that's V, that's voltage. Voltage equals the reciprocal of a time constant. No, that's nonsense because V is in volts and 1 over RC is in hertz. Well, radius per second. I expect a high school physics student to be able to answer this question. What is frequency equal to?
I mean, I guess you asking the meaning of frequency, what is equal to 1 over 2 pi RC?
No, I didn't ask. You came late, so you don't know what I asked. I said, how can you find frequency from this graph?
What would it have to do with how long it takes to reach a steady state?
Absolutely not.
Pardon?
No. Your answer makes no sense at all. What is frequency equal to?
Is it, let's see, is it like the voltage divided by the time it took for one cycle?
No, that's not what frequency is equal to. Frequency does not equal voltage divided by period. What is F equal to?
Is it 1 over the period?
It is 1 over the period. Every high school physics student knows this. It's 1 over the period. You've known this since 120. You've known this since 120. Now that you need to apply it, you can't apply it. So let's measure the period. We don't want to measure period up in here because it's not quite a sine wave yet. It's a sine wave back out here. So I'm going to take this first crossover. So I want when that is 0. There it is, 0. And I need to move this out of the way. And I select the time. I select the point. Okay. And the time is 15.853 nano. And then I need to select the end of that period. And so now I am able, out of the way. I am able to read the period. And the period is 17.27278 times 10 to the minus 9 minus 15.853 nano. Is that N or M? No, it's milli. Milli. 10 to the minus 3. So that is that is 1.425 times 10 to the minus 3. So the reciprocal of that is 701.8 hertz. See there? The period is the end of the end of the cycle minus the beginning of the cycle. That's the period. We take the reciprocal of that, we get the frequency. Okay. Which, by the way, is very close to the design frequency, which was 704.
Dr. Cartwright,
Yes.
did you get this same answer when you did the other graph?
No. Why not? Let's do the other graph right now. Okay. Well, the problem with this is I can't read it. But believe it or not, somebody submitted this to me. Somebody submitted a graph just like this to me, and expect me to read it. Let me first of all get
Dr.
rid.
Carter, I didn't know you could change the. You see how you did the cursor? Yeah, when I try to drag my own mind, is when it don't move.
What are you talking about?
You see how you press the mark for the, I think it's called the toggle of the cursor. That's how you get in. Yeah,
that?
right there.
What
yeah,
about
so
it?
You was able to move the numbers, or where you marked it, you was able to move that.
With the arrow keys. I told you that a long time ago with the arrow keys.
Yes, sir.
But you see, y'all don't listen to what I say. Okay, let's take FFT of that. Okay, clearly we can't read that. So we have to change the scale. I'm going to make that one kilohertz. Okay. And there I have just one sine wave. And what's the peak of that? Let's find the peak. You move in the arrow keys. Let's find the peak. 8.86, 8.89, 9.3, 9.6, 9.03, 9.07, 9.07 seems to be the peak. What does that say? That says 699.95. Okay, that's 700. It says 700. It is very close. It is very close to the other reading, but it's not exactly the same reading. Now, let me tell you what. Let me tell you why some of you didn't get good reading on this. Because some of you all stopped way back here. You didn't let your signal go until it reached steady state. Okay. If it hasn't reached steady state, then it hasn't reached a sine wave. This back, the front part of it's not just a sine wave. It looks like sine wave, but it's increasing with time. You have to wait till it reaches the sine wave, and then you could do the FFT. Because what the FFT does is it measures the last period. Okay. And if the last period is back here, then you got a waveform that is still changing. Okay. Any questions about that? All right. Is there no other questions about the assignment? I'm going to move on. I don't want to use, I want to make another oscillator, but I don't want to use a non-inverting amp. I want to use an inverting amp. So what do I need? An inverting amp. So what do I need for my feedback network? What must my feedback network achieve for me? For oscillation, what must the inverting the feedback network achieve for me to have oscillation?
Well, in this case, we would need a negative gain, something probably more than -3. So something lower than -3, yeah. dB.
You're not answering my question. Did I ask you about the amplifier? Did I ask you about A? Or did I ask you about beta? You have to listen. I asked you about beta. So why are you telling me about A? You're telling me about A because you didn't listen to the question. I asked, what do we need beta to accomplish for us? What must be the primary thing that beta does for us? Folks, I don't know why y'all can't answer questions. I don't know why y'all can't think logically. I don't know why y'all can't solve problems. What do you need for oscillation? Tell me again, what do you need for oscillation?
You need it to be equal to 1.
You need what to be equal to 1? What do I need to be equal to 1?
The product of A and B.
A and beta. That's not a B, that's beta.
Beta.
I need A beta equals 1, 0. That's what I need. Or 1, 360. Because angle of 0 is the same thing as the angle of 360. We can't distinguish those two. So now what do we know A? We know A is some numerical value. A is the magnitude of A. What's the angle of A? What's the angle of A?
Zero.
Why? Why is the angle of A 0?
And it's because it's a non-inverting amp.
Is that what I said?
I can't remember exactly what you said.
I said this is an inverting amp. That's what I said. Because last time we used the Williams Bridge oscillator, which was a non-inverting amp. This time I want to do something different. I want to use an inverting amp. So what's the angle of A? Wow. We just did this last class. Which is last Friday. If we have an inverting amp, what is the phase shift?
If you have an inverting amp, that means, sorry, the phase shifting in 180.
The phase shift is 180. The phase shift is 180. So what do we need from beta? So beta must have amplitude and beta must have angle. What do we need? What do we need from beta? From beta, the feedback. What do we need?
And the angle should be negative 180.
Negative 180 or positive 180. That's the same angle, isn't it?
Yeah. And
so theta. Theta must be 180 or negative 180. Okay. If it's 180, then we'll have 360 degrees.
So
If
that
it's
means,
negative 180, yeah, go ahead.
so does that mean beta should be 1 over the magnitude of A?
That's exactly what it means. The magnitude of A times the magnitude of beta must equal 1. We've been through this last class. But the primary thing right now, what we need from beta is what? A phase shift of 180 degrees or negative 180 degrees. How do we get a phase shift of 180 degrees? What network, what circuit will give you a phase shift of 180 degrees?
You say what network gave a phase shift of 180 degrees?
I answered first.
And we said that was an inward now.
What network, what circuit gives you 180 degrees at just one frequency? We want just one frequency because we want this to oscillate at just one frequency. Just like the homework you're trying to do today.
So you want RC high pass filter.
Really? There's a high pass. What's the maximum phase shift you can get from a high pass filter? I assume you mean a first order high pass filter. What's the maximum phase shift you get from a first order high pass filter?
Not around, that's 90.
90. So what you gonna do about that?
You gotta double it up.
What does that mean? What do you mean by double it up? What are you gonna do to double it up?
So that you don't mean in the all pass.
You can't have all pass filter. Because all pass filter does not give you a phase shift of 180 degrees at one particular frequency. It gives you a phase of 180 degrees either at DC or at infinity, and none of those you can use. So I ask again, what network are we going to use? What circuit are we going to use to get a phase shift of 180 degrees at a particular frequency? How do you add first order high pass filter to give you a maximum phase shift of 90 degrees? Where? A DC. Well, that ain't gonna work. That ain't gonna work for two reasons. We need 180, and it can't be DC because DC is not a sine wave. I hope you all got a snip of this because I'm going to change pages. We cascade. Fourth order filters. We cascade first order filters. And that means the phase shift would look like this. The phase shift would start off at 270. At 270 at DC. Right. And 0 degrees. And somewhere between 270 and 0. Zero would be at omega equals infinity. Okay. There'll be 180 degrees. There'll be 180 degrees. And there's our resonant frequency right there. There's our resonant frequency. Now, how do we find this? How do we find it, what frequency this is? What's the procedure we use to find that? All right, let's go back to the Wien-Bridge oscillator. Let's go back to the Wien-Bridge oscillator. What do we have with the Wien-Bridge oscillator? All right. What we had was phase was this. We needed a phase shift of 0 degrees. This was 90 degrees, and this is negative 90 degrees. Okay. This is the phase. This is the phase of the transfer function of beta. And corresponding to that was the magnitude. And the magnitude was doing this. And this is all oscillation frequency where we have 0 phase shift. Why? We need 0 phase shift because the amplifier gave us 0 phase shift. And this amplitude was a third. And here's F0. Right. And I gave you this answer. I'm telling you, when we got 0 degrees phase shift, that was at 1 over 2 pi RC. And I just gave you that result. And this is the magnitude here. All right. Now this F0 and that F0 has to be the same F0. That's what we did for the. And what was beta? What was the transfer function for the feedback network? The feedback network. What's this? VL phasor divided by VI phasor. There's VI phasor. And there's VL phasor. This is R, this is 1 over SC, this is R, and this is 1 over SC. And how do we find the transfer function of this? How do we find the transfer function of this? Nobody could tell me how to find the transfer function of this?
What you have to do them two sections at a time. Like
I don't know what that means. What does that mean?
like our first part, you could name that Z1, and the second, the with the R and 1 over RC, but in series.
Which one you call in the series?
The part right to the top with the R. And
That's Z1.
Yeah.
That's in series.
Yeah,
That's
that's what I mean. That in series, and the one in parallel, you could name that Z2.
Okay.
And you could work out Z1.
What's Z1 equal to?
R plus 1 over SC.
R plus 1 over SC. And what is Z2 equal to?
R times 1 over SC divided by R plus 1 over SC. And then
Multiply top and bottom by SC. R over SRC plus 1. That's Z2. And so what is beta equal to?
that would be C1 plus C2.
Really? The transfer function is Z1 plus Z2. Miss Buchan, what's the transfer function?
Now, once we find the Z1 and Z2, you can do the same product over sum again.
Really? The transfer function is Z1 times Z2 over Z1 plus Z2? You know, y'all gonna graduate not knowing anything. The transfer function is Z2 over Z1 plus Z2. We did that a million times. A million times. So that's R over SRC plus 1 divided by R plus 1 over SC plus R over SRC plus R, which is R over R plus 1 over SC, SRC plus 1 plus R. And then we can multiply it top and bottom by SC, SC plus 1, SRC. And that'd be SRC over S squared plus 2 SRC plus 1 plus SRC. And then finally, simplifying that, it's SRC over S squared, R squared, C squared. Plus 3RC plus 1. That's the transfer function. That's the transfer function. And the magnitude of this transfer function is given by this curve. And the phase of this transfer function is given by this curve. That's for the Wien-Bridge oscillator. Just like we get a transfer function for the Wien-Bridge circuit, we get the transfer function for this circuit. That is more complicated. Okay. For the Wien-Bridge oscillator, we wanted a phase shift of 0 degrees from our network. This is going to be called a phase shift oscillator. A phase shift oscillator. Okay. Uses 3 first order high pass filters cascaded. We want a phase shift of 180 degrees. We want a phase shift of 180 degrees, and that for this network that occurs 1 over 2 pi RC root 6. That's where that occurs. Okay. And corresponding to the frequency at which we have 180 degrees, we have a magnitude. We have a magnitude of 1 over 29. 1 over 29.
Where did you get root 6 from in the denominator of?
Do what I said. Find the transform function of this and then set the phase to 180, and you find that's true. That's where it comes from. Say again? Did somebody say something? Find the transfer function of this network. Find the phase angle. Set the phase angle to 180. And then when you solve for f, you will get 1 over 2 pi RC root 6. And when you have a phase shift of 180, the amplitude, the magnitude of transfer function is 1 over 29. So what must the gain be? What must the gain of the inverting amplifier be?
The gain must be 29.
Yes. Yes. That's exactly right. And this is how all oscillators work. You must have the right phase. You must have the right the loop gain magnitude must be 1. Okay. So now what accomplishes that? What's that circuit look like? Now, instead of going ground here, we go to the virtual ground. Remember, this is the virtual ground? All right.
So the virtual ground, or
And this output goes back to this input. Okay. And this is R, and this is R, and this is R, and this will be RF. So this is C, this is C, and this is C. Okay. And the oscillation frequency would be 1 over 2 pi RC root 6. And RF of R must be what? 29. Why? Because that oscillation frequency, okay, this output to here, okay, that's 1/29th. That's 1/29th of whatever this is. Okay. If we call this voltage here, we call it Vn, then the voltage across this resistor here be 1 over 29 at Vn at the oscillation frequency, and then we step it up. We step it up by gain of 29, so this voltage here be Vn. So V out equals Vn, and that's what we need for oscillation. This is called a phase shift oscillator. Now, just like the gain had to be more, than 3 to get oscillation started. And then when the oscillation gets started, the gain has to be less than 3. The same is true here. The gain has to be greater than 29 to get it started, and then we can reduce the gain after the oscillation starts. And so we'll end up with, give me a second. Are you seeing a PDF file?
Yes, sir.
Oh, okay. All right, there it is. Okay, there it is. In this case, we're using 4 diodes. Why are we using 4 diodes? Because we want the output to increase to 1.4 volts before turning on. Okay. So as you can see here, when the diodes are off, what's the gain? When the diodes are off, what's the gain?
$32.
You get negative 32.1.
Yes, negative 32.1. Because when the diodes are off, the RF is 698 plus 200. 698 plus 200, that's 898 divided by 28. That's 32. Okay. So the gain is more than we need. So oscillation starts. And then once the oscillation begins, the diodes turn on. And when the diodes turn on, what's RF?
RF is R4 in parallel. R4 plus the answer would, because R6 and R5 could be in parallel. And you have to put that over R3.
And how much is that?
Negative 27.
So it's 82.5 plus 200 reciprocal times 82.5 times 200. Plus
I get
68
negative 25.
divided by 28. No, it's negative 27 like he said. It's negative 27 like he said. Okay. Any questions about this? Yeah, see it here? See it in his write-up? It's negative 68 plus 200 in parallel with 82.5 divided by 28. That's negative 27. Let's go
So
back.
when the diodes are on, the gain increase.
Say again?
So that means when the diodes are on, the gain increase?
No, the gain decreases.
I see it going from
Gone from 32 to 27.
So that doesn't mean it increase?
No, if it goes from 32 to 27, how does that increase? I mean, the magnitude of it.
Oh, the magnitude of it, yeah. I thought you were looking at the negative sign.
No, we talking about the magnitude. What you Yeah, see there? See the formula there? For oscillation? All right. Any question about this phase shift oscillator?
Will we be required to actually work out like the transfer function of it?
For this phase shift oscillator?
Yes, sir.
No, I won't do that to you. But for the Wayne Bridge, yes. For the Wayne Bridge, yes, or even for the one I gave you for last year's final exam. Have you all looked at last year's final exam they sent you?
Didn't have a chance.
I look at
Well,
it.
you better find a chance. You better find a chance because the final exam's in 2 weeks, isn't it?
Last week after next Friday.
The final exam, it's the 14th.
That's on,
Yeah,
that should be on Friday. Right?
Saturday is the first.
yeah. Next Friday is the 7th, and then the Friday after that, it's the 14th. So if you don't have a chance yet, you better find a chance.
So I mean, we ain't having no more assignment.
No, you're not having more assignments. I gave you, well, how many assignments already I gave you? I gave you at least 8.
4 take home, 4 assignments, and then
Yes.
1 midterm.
Yeah. But I'm only counting 3. I'm only counting 6, 3 of each. Because I replaced your worst homework with assignment 4. And I'm going to replace your worst test with today's test. Okay. Any other questions? No, I am not going to make you do this, but I will tell you it could appear on your final exam. Okay.
Yes, sir.
So I suggest you take the rest of this lesson and do the simulation. Set yourself the job. Pick a frequency that you want to oscillate at, and see whether or not you can achieve that. Okay. But I'm not going to grade it.
Will you be able to check it?
Why would I have to check it? Would it be obvious to you whether or not you've done it?
Yeah, you're right. Piece by piece numbered right.
If you did it right, you'll know.
But if you have a question about it, if it ain't coming out right.
Well, if it ain't coming out right, you're doing the piece by piece wrong. Or you got the formula wrong. I gave you the formula. Okay, you script the formula. All right. That's all I wanted to do for today. Any questions before I say goodbye?
Yeah, for the homework. When I came there, they see only had the output on, so we have the input on. We getting points off.
Say again?
For the homework where you were simulating for the output voltage coming out of that. I'm saying if you had the input voltage, would you get it wrong?
Why you give me the input voltage and not the output voltage?
I give you. For my case, I put both.
Well, if you did both, then it won't be wrong. No.
All right.
You're going to take the output from this from this device at the output. You're not going to take the output from the input. So you want to see what's happening at the output.
Yeah. When I do it, I like to see both to compare it.
Well, that's fine as long as the output is readable. Any other questions? Well, I'll see you on Monday. Have a good weekend.